OK, so what I'm going to do today and tomorrow is talk about quantum error correction. So if you think back to the first week, you remember that I was talking about implementations that tended to have a time scale of 10 to the 3, 10 to the 4 between the decoherence times and the gate times, and error rates that are like probably at the current error rates are more than about 10 to the minus 3, 10 to the minus 4, which means that if you do about 1,000 gates, or certainly at least 10,000 gates, the likelihood of getting an error in there somewhere is quite high. But then if you think about the algorithms I've been talking about, they tend to need quite a lot of gates, certainly a lot more than 1,000. So for instance, Shor's algorithm is about n cubed gates in the simplest version of it, order n cubed, so there's a constant factor as well. And RSA on typical implementations today will have at least 1,000-bit numbers. So we're talking 10 to the 9th gates in order to get anything done, right? And well, Shor's algorithm requires a lot of gates. The Hamiltonian simulation that you saw requires fewer. But still, when you start to add up the actual numbers, it tends to be much bigger. And 1,000 gates is really not very much. And so in order to make a big quantum computer work and give you the right answer, we're going to need some way of dealing with those errors. Now, one approach is just to say, OK, come on, experimentalists, you have to work harder, get those error rates down. And they are, and they're trying to get them down. But at some level, this becomes an unrealistic goal. And we need software to come in order to fill the gap. And that's where quantum error correction comes in and the theory of fault tolerance. So mostly I'll be talking about error correction. But fault tolerance is important as well. And so quantum error correction is really just for the communication scenario. So we have Alice and Bob, again. And Alice wants to send a qubit to Bob. And unlike in the cryptographic case, this time there's no eavesdropper, but there is an environment that's adding noise. OK? And we're assuming at this level, for purposes of quantum error correction, that Alice and Bob have perfect quantum computers that interface with their communications device. So Alice can encode her qubit however she wants. Bob can decode, make whatever measurements are necessary, and so on. And the only source of errors is in this communications channel between them. So fault tolerance takes quantum error correction and goes one step further, where you no longer assume that Alice and Bob have perfect quantum computers. So really, there's no Alice and Bob anymore, because we're thinking of just Alice doing some computation. And all the gates that she's doing and all the state preparations and all the measurements, they can have errors in them as well. OK? So this is a whole protocol that we have to layer on top of a quantum error correcting code. And it gets fairly complicated, the details of how you do that. So that's why I'm not going to go into much detail. But first, we have to talk about quantum error correction and how you can do that, and what are the principles behind that. So I guess I could also say that I've written this as a communications channel, but you can also think of it as just storage, right? So in that case, Bob is like Alice's future self. Alice has a qubit. The decoherence rates are low enough that she can encode it how she likes without having to worry too much about errors. But she wants to store it for a very long time. And during that time, there's likely to be errors. And at the end, she wants to be able to correct those errors. So this basic problem, of course, occurs in classical information as well. And classical computers are so reliable that the error rates per gate are negligible. And so error correction and fault tolerance are not really widely used in classical computers. But in classical communications, that's not true anymore. And in fact, error correcting codes are vital to all of our modern high-speed communications. It just wouldn't be possible without really sophisticated error correcting codes that are built into all the communication software. And it's also used to a certain extent, much lesser in terms of static memory, like hard drives and DVDs and stuff like that. OK, so let's therefore think about classical error correcting codes, just briefly, as kind of a way of understanding how error correction works and where we have to go to do quantum error correction. So the simplest classical error correcting code is a repetition code. And the repetition code takes a 0 and encodes it using 2 extra bits, so it becomes 3 zeros. And a 1 gets encoded as 3 ones. OK? So suppose Alice sends one of these 2 messages through the channel to Bob. And Bob receives something that looks like this. He gets 0, 1, 0. OK? So what does he do? Well, he says the communications channel has errors in it, but the error rate is not too high. So I think it's more likely that there was just 1 error here rather than that there were 2 errors in the first and third bits. So probably this started out as 0, 0, 0. And so the message was 0. OK? So to be a little more concrete, suppose we have independent errors on every bit that's sent through the channel. And they happen with a rate p. So with probability p, a bit that goes through this communications channel is flipped. And with probability 1 minus p, it stays the same. OK? So then the probability of no errors is 1 minus p cubed. Right? The probability of 1 error is p times 1 minus p squared of, say, an error on the first bit and no errors on the second and third bits. But it's the same for having a single error on the second bit and not on the first and third, or on the third bit and not on the first. So there's actually three possibilities like this. So we have 3 times p 1 minus p squared. And then the probability of having 2 errors by the same sort of argument is 3p squared times 1 minus p. So let me just kill those. And the probability of having 3 errors, of course, is p cubed. OK? So if you look at this, if p is small, then this thing is order p, this thing is order p squared, this thing is order p cubed. And when p is not that small, it's possible that this thing is bigger than this, right, because of this factor of 3. But when p is small, it's always going to be smaller. And more importantly, this thing here is going to be smaller than this thing here. And so if Bob makes his decision, as I've said, where he says, oh, it's more likely that 1 bit was flipped than that 2 bits were flipped, he's going to be right most of the time. And the smaller p is, the more often he'll be right. And the point is that the probability of getting 2 errors, the case where Bob deduces the wrong thing, is O of p squared. Whereas the probability of having an error, if they hadn't done any error correction at all, is p. OK? And when p is small, this O of p squared thing is substantially less than p. And so by using the error correcting code, they've reduced the error rate, the probability that Bob is deducing the wrong message. OK? Does that make sense?
So what was the last statement again?
So if they hadn't used the error correcting code, the probability of error would be p. But they did use the error correcting code. There's still a chance of error if there's actually 2 errors that occur in the channel. But that's order p squared. And when p is small, that's less than the probability if they had not used the code at all. Probability of error. OK? Yeah?
Does the fact that we need more bits now change anything?
Yeah, well, it changes two things. First of all, it means that they can't send messages as many messages with the same number of uses of the channel. Right? Before they could send, if they used the channel n times, they could send n bits. Using this particular code, they could only send n over 3 bits. But they're more reliable. Now, it is true that so the fact that we're using more bits also affects this factor of 3. That's where the factor of 3 is coming from. And what that means is that it's not good enough that p is less than, so p should always be less than a half, basically. Otherwise, it's more likely that it's flipped, and so you just take that into account. But if it's a half minus a little bit, then this is actually bigger than this because of that factor of 3. And so that's the other cost of using more bits. Now, people have come up with much more efficient error-correcting codes so that if you're using the channel many, many times, you don't get this factor of 3. You just get kind of a relatively small loss of the number of uses that you can make. And how many depends on exactly what the error rates are. But I'm not really going to go into that. OK? Any other questions about this? Yeah. Sorry, say again?
Why is it order p squared when you apply that?
Oh, yeah. So if we have these two situations, then Bob correctly deduces what the message that Alice sent is. And so it's in these two situations that Bob is wrong. OK, so what's the total probability of these two things? It's order p squared. OK? Anything else? OK, so now let's start to talk about quantum error-correcting codes. So we might say, OK, we want to make a quantum error-correcting code. Let's use this as inspiration. And we'll encode our quantum state psi as 3 copies of psi. OK? So does that seem like a good idea? No. Why not? No cloning theorem. Yeah. So so when you start to think about quantum error correction, there's all sorts of problems that crop up if you try to take these classical ideas and apply them. The first one is this no cloning theorem. And so another one that you can see if you kind of look more closely at this classical thing is, well, how did Bob do the decoding? Well, he looked at the bits that he was getting, and he said, oh, the second one is different from the first and the third ones. But looking at the bits is a bad idea when they're qubits, right? Because you'll collapse the superpositions. OK, and then there's more problems as well. So for instance, you might say, well, OK, suppose we somehow were able to deal with those problems, and we come up with a quantum error-correcting code. Well, but it's this code, what does it correct? It corrects bit flip errors. And that's not enough, right? For a quantum code, we also need to be able to correct phase errors. Because phases are really important for making the interference work right. And moreover, that's not the only type of thing that can happen to a quantum state, right? We can have continuous rotations by any angle. We can have decoherence that transforms a pure state into a mixed state. But somehow we've then got to get it back to a pure state. And really, there's an infinite spectrum of possible things that can happen to even just to a single qubit. OK? So looking at this list, you might reasonably be discouraged and think that quantum error correction is not going to be possible. But obviously it is, because I told you I'm going to give 2 lectures on quantum error correction, which would be kind of pointless if it were not possible. OK, but are there questions on this so far? Bearing in mind that we will, of course, deal with all of these eventually. OK, so OK. So let's start our attack on these. Actually, let me do this on the other board, on the other side. Be a bit easier. So let's start our attack on these by making a quantum version of that repetition code. OK? And so let's just forget about problems 3 and 4. Right? They're talking about correcting different kinds of errors. We want a quantum code to correct bit flip errors. And what about this classical repetition code fails? I mean, that corrected bit flip errors. What happens if we put kets around those things? Shouldn't it still correct bit flip errors? Right? It could still function at least as a classical code. Right? So concretely, we could say I'm going to encode a qubit, alpha 0 plus beta 1. Well, if I'm encoding 0 as 3 zeros and a 1 as 3 ones, then that has to go to the superposition alpha 0 0 0 plus beta 1 1 1. OK? And I mean, in some sense, this is still making 3 copies of the state. But it's only making 3 copies in one basis. And that's how we're getting around the no-cloning theorem. OK? We can copy things in one basis, in this case, the computational basis, but not in arbitrary bases. So this is not alpha 0 plus beta 1 cubed. And that's how we get around the no-cloning theorem, or at least that's how we do in this particular case, which is we don't try to copy it in arbitrary bases. We might want to try to copy it in some basis. And another way to think about this is we're using entanglement, right? This is an entangled state when alpha and beta are both non-zero. And a way to think about it is we're spreading the information out about the state rather than just kind of confining it to a single qubit.
I have a question.
Yeah.
If one of the coefficients is 0, then aren't we violating the no-cloning theorem?
No. So if one of the coefficients is non-zero, then it's not an entangled state. But again, that's just copying it in one basis, right? So it's the only case where you're getting 3 copies of the original state is if one of the coefficients is 0.
Yeah.
OK? And so that's just saying that there's 2 particular orthogonal states, 0 and 1, that do get copied, and that's allowed. It's the arbitrary superposition. Remember, you remember the proof of the no-cloning theorem said, well, we could have some state psi that we're copying and some state phi that we're copying. But then if we try to also copy psi plus phi, that's when we run into trouble. So copying 0 and 1 are OK, because they're orthogonal. But superpositions of that are not OK. OK? Any other questions? OK, so now let's move on to problem 2. So how are we going to, we want to correct bit flip errors, but how can we do that without collapsing the superposition, right? Because if we do have to measure all the qubits and see, oh, one of them is different, then we're not preserving a qubit. We're really just preserving a classical bit. And it's not really a quantum code. So, but let's think a little bit more about what we actually have to do to see where the error is, right? What's important is that, well, OK, so let's suppose we have a bit flip error on this state. So then what do we have? Suppose it's a bit flip on the second qubit. So 0, 0, 0 will become 0, 1, 0. And 1, 0, 1, 1, 1 will become 1, 0, 1. OK? And sure, if we measured all 3 qubits, we would see that the second one was not consistent with the first and third. But you'll notice that that's true in either case. Right? Whether we have the encoding of 0 and the encoding of 1, the second qubit is not the same as the first and the third qubits. And that's a property that's independent of whether we have the logical 0 or the logical 1. And so that's something that we can, in principle, measure without measuring whether we have a logical 0 or a logical 1. So how do we do that? Well, so we have the 3 qubits of the code. And what we'd like to do, we can break down the question of whether of which qubit is different into 2 steps. We can say, are the first 2 qubits the same or different? So we're going to take an ancilla that starts at 0 and do C0s from the first 2 qubits to that ancilla. And then we're going to measure that ancilla. OK? And so if both of these are 0, then this is still 0. If both of them is 1, then this gets flipped twice, and it's 0 again. But if one of them is 1 and one of them is 0, then this is a 1. OK? So this tells us if the first 2 qubits are the same or different in the computational basis. OK? And then we can do the same thing to see if the second and third qubits are the same or different. OK? And so let's look at what happens when we get, so these 2 measurement results are called the error syndrome. Because looking at them tells us information about the error. So in particular, there's 4 possibilities here. So if it's 0, 0, 0, 1, 1, 0, 1, 1. So if it's 0, 0, what does that tell us? All of them are the same, right? And going back up there, we're going to say, well, either if all of them are the same, that means that either there were no errors or all 3 bits got flipped. OK? And that's very unlikely that all 3 bits got flipped. So let's assume that there's no errors. So what about 0, 1? What does that imply? Yeah.
Error on the third qubit.
Error on the third qubit, right? Because the first 2 are the same, and the last one is different than the second one. And so it must be the third one that got flipped, assuming there's only 1 bit that flipped. If there's 2 bits that flipped, then it would be the first and the second. But if there's 1, it has to be the third. And again, that's more likely. So often when you're dealing with quantum error correcting codes, you're going to say, OK, I want a code that corrects some number of errors, in this case, one error, in this case, one bit flip error. And you're just going to assume that that's how many errors there are, right? And the logic behind this is what I did before, that one error, is reasonably likely, two errors is less likely. So I'm just going to kind of always assume that if there's an error synchrome that's consistent with one error, that's what it is, even though it could be something else. OK, similarly, 1, 0 tells us that the first bit is different from the second and third bits. And therefore, it's probably the first bit that had the error. And 1, 1 tells us it's the second qubit that's different. OK? And notice that these error synchromes don't depend on whether we had the 0, 0, 0 state or the 1, 1, 1 state, right? So we're getting information about the error, but we're not getting any information about the encoded state, which was what we wanted, right? And so when we do this measurement, we don't collapse the superposition between these two branches. OK? So the bottom line is that we can measure the error synchrome without measuring the encoded state. OK? Yeah.
So, I mean, I guess the linear algebraic idea is that since we're expanding the Hilbert space, we are finding some new operator which commutes, say, with the observable that we're interested in, and that we're measuring this new operator.
Yeah, I mean, the expanding the Hilbert space part is useful, but it's not actually essential for this. So what you could sorry, I mean, I guess it depends what you mean by expanding the Hilbert space. We're expanding it to an 8-dimensional Hilbert space. In here, I was expanding it even more by adding some ancillas. But in the 8-dimensional Hilbert space, our qubit is just a 2-dimensional, a logical qubit is just a 2-dimensional Hilbert space. So we have some 2-dimensional subspace that's encoded in this 8-dimensional Hilbert space in such a way that there's some measurement we can make that's kind of orthogonal to the direction of this subspace, and will only tell us about the errors. OK. So anyway, so this takes care of our second problem, right? It definitely shows us that we don't have to measure everything. We don't have to collapse the logical superpositions in order to protect qubits against errors. OK? So are there any more questions about this code? Yeah.
If there's like, are we always assuming that the bit flip kind of happens or it doesn't? It's never in a superposition of it getting flipped?
Yeah. At the moment, we're assuming that. Well, that type of thing is down here in 4. So the moment I'm just assuming, probability p, there's a bit flip error, probably 1 minus p, there's no error. And then when I go to step 3, to problem 3, I'm going to do something similar for phase errors. And then the more general case is at the bottom.
So these measurements never collapse anything? Yeah, it's all right.
That's right. That's right, yeah. Any other questions? OK. So so this is bit flip errors. That's great. But if you look at this code, it certainly doesn't help against phase errors. And actually, it makes phase errors worse. Why is that? Well, suppose you have a z error on the first qubit, right? It'll take it to alpha. The state will become alpha 0, 0 minus beta 1, 1, 1. OK. And that tells you why this doesn't correct. You can't correct that, because that's also a valid code word. Right? So there's certainly nothing we can do to tell whether it was supposed to be plus beta 1, 1, 1 or minus beta 1, 1, 1. But moreover, if there's a 0 on the second qubit, you get the same thing, alpha 0, 0, 0 minus beta 1, 1, 1. And same with the third qubit. And so not only does this not correct phase errors, but now a phase error on any of the 3 qubits which is almost 3 times as likely, will ruin the state. So this code has created the protection against bit flip errors for protection against phase errors. So we're going to have to try to get around that. But the first step is just to come up with a code that corrects phase errors. And we're not going to worry about bit flip errors. So how are we going to do that? OK, so the main idea here is that the Hadamard transform, what does it do? Well, it maps the 0, 1 basis, which are eigenstates of the Z operator, to the plus minus basis. And vice versa. And so this is taking the eigenstates of Z to eigenstates of X. So this Hadamard is kind of switching the roles of X and Z for the Hilbert space. And before, we had a code that corrected a bit flip error. That's an X error. Do I need to write down the polys again? Let me do that, because we're going to use them a lot. So of course, we have the identity. We have X. We have Y. And we have Z. So X is a bit flip error. And the Hadamard switches its role with the role of Z, which is a phase error. OK? So if we do the Hadamard and everything, then this code that corrects bit flip errors should now correct phase errors. So in particular, suppose we encode alpha 0 plus beta 1 as alpha plus 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 beta minus minus minus. OK? And now suppose that there's a phase error on, say, the first qubit. Now what's the state? Well, now it would be alpha minus plus plus. Here. And now you see that in this Hadamard rotated basis, the first qubit is different from the second and third qubits. So if we do that whole circuit up there, but with everything rotated by Hadamards, then the error syndrome will tell us, oh, it's the first qubit that's different, which we'll deduce is a phase error on the first qubit. OK? So everything works exactly the same way as for the previous error. We're just doing it in a different basis. OK? Does that make sense? So this is then a 3-qubit phase error correcting code. But of course, it has, because it's really the same code as this bit flip code that I showed you, it has the same drawback. Namely, it corrects phase errors, but it makes bit flip errors worse. OK? So how are we going to get around that? Well, first, are there any questions on this phase code before I do that? OK, so how are we going to get around this? Well, we're going to have to go to more qubits. So in particular, this is the 9-qubit code, also known as the Shor code. He's the one that invented it. And what does it do? Well, it encodes 0 as 3 copies of 0, 0, 0 plus 1, 1, 1. And then 1 as 3 copies of 0, 0, 0 minus 1, 1, 1. So if you look at this, and of course, if you have a superposition, alpha 0 plus beta 1, here, so sometimes I'll write these things with lines over them to indicate that they're the logical bits. And then alpha 0 plus beta 1 will get encoded as a superposition alpha 0 bar plus beta 1 bar. OK, so while we have 3 copies, again, this is just in one basis, right? And the real thing that encodes a superposition is some 9-qubit entangled state. Okay, so if you look at the structure of this thing, you see it's kind of incorporating, in some sense, both the bit flip repetition code and the phase repetition code. The bits are getting repeated in sets of 3 here in the standard basis, and the phases are getting repeated between the 3 sets here. Okay, so if we have a bit flip error, we can see that in exactly the same way as before by measuring within each set of 3 if one of the qubits is different from the other 2. Okay, so if we have a bit flip error on any of the 9 qubits, we can definitely see that. And if there's a phase error, well, what is that going to do? It's going to change one of these phases to be different from the other 2. And so for this, we need a bit more complicated circuit, which I'm not going to show you in detail, although we'll talk a little bit more about it later, maybe tomorrow, maybe later today, maybe tomorrow. And you'll see that the phase is different from the other 2 phases. Okay? And that, again, is true, equally true for the logical 0 and the logical 1. So that's something we can measure without measuring the encoded state. So we can correct both a bit flip error and a phase error. OK? That was our goal. And actually, we've gotten a little bit more for free, right? Because the Y error is both a bit flip and a phase error. And those things are corrected separately here, right? The Y will both make one of the bits different from the other. In the standard basis, flip a bit in one of the qubits that will pick up with the X check, the check for bit flip errors. And it will change a phase. And we'll pick that up when we check for phase errors. Okay? So we're also correcting the Y errors. So any single qubit bit flip error, phase error, or Y error gets picked up by this code. And of course, it can also correct a bit flip error on each of 2 different sets of 3, or a bit flip error on 1 qubit and a phase error on a different qubit. All that's true. But there are 2 qubit errors that it doesn't correct, like 2 bit flips in the same set of 3. OK, so in general, it corrects 1 Pauli error. And that's what makes it a good quantum error correcting code. And it gives us an example of a code that's solving this problem 3. OK? So any questions about that? Yeah.
In classical computing, there's something like memory speed trade-off in algorithms. Is there something similar here where some formal notion that we have to go to a larger number of qubits in order to correct?
Yeah. So there's certainly in the communications context, there's a very well-defined notion of channel capacity, classically and quantumly. Quantumly, it's much harder to compute. In fact, we don't know how to compute it. But the idea is that if you're using your quantum channel n times, well, OK, there's various different ways you can approach it. But if you're using the channel n times, and there's some there's a capacity of that channel as a function of the noise, which says that if you want the logical error rate to be 0 in the limit of using it many times, then then you have to use it at most at some rate that's the capacity. So for instance, out of every qubit that you send through the channel, you can send 0.75 qubits of information. Okay, so if you use a channel 400 times, you can send 300 logical qubits. There's a similar bounds that you can set, upper lower bounds, if your goal is just to correct arbitrary errors of up to a certain size, rather than kind of the most typical errors. It's similar, but not the same. OK? Any other questions? Yeah.
Is 9 the best you can do for being resilient?
It is not. So I'll almost certainly tomorrow I'll show you some more fiction codes. OK. So any other questions on this 9-qubit code, at least as far as it corrects poly errors? OK. So we've solved problems 1 through 3, but we're still facing problem 4. So now we want to correct continuous rotations. We want to correct decoherence. We want to correct all the possible things that can happen to a single qubit. And in order to go from correcting just bit flip errors to correcting both bit and phase errors, we had to increase the number of qubits from 3 to 9, although we don't quite have to go that far. But we do have 3 is not enough to correct both bit and phase errors. And now we want to correct an infinite set of errors. So if we had to add more qubits to correct more errors, does that mean we're now going to have to go to an infinite number of qubits? That would be bad. But instead, let's do something that really seems kind of stupid, which is to take this 9-qubit code, which we designed to correct poly errors, and just see what happens with it when we have some other error. Okay, and just try to correct it as if the error were actually a poly error. OK, so how are we going to do that? So let's take a concrete example and see how it works out. So I'm going to do the unitary R2 theta, which I had defined as this, a diagonal gate that does a phase rotation on 1 relative to 0. And I'm going to pick 2 theta for a reason that you'll see in a minute, because I want to rewrite this as e to the I theta times e to the minus I theta and e to the I theta here. And of course, this doesn't really matter. That's just a global phase. So I'm going to ignore that. And so up to that global phase, we can write this form of the gate as cosine theta times the identity, minus I sine theta times z. OK? So let's see what happens when we do this on 1 qubit for the 9-qubit code. Suppose we do this R2 theta. So the superscript is going to say that we're doing it on the jth qubit. And psi is going to be some state of the 9-qubit code. And then we're going to have some ancilla qubits that we're going to use to eventually use to measure the synchrone. We haven't done that yet. OK, so what's the state at the point before we do any error correction? So the error has occurred. We're going to expand this R2 theta this way. So we have cosine theta identity applied to psi is just psi. And then by linearity, we can just add the effect of this thing, which is z on the jth qubit applied to psi. OK? Is that Make sense so far? OK. And so now I want to step through the error correction process. So first, the error correction basically consists of 2 steps, right? So one is we do some gates interacting, quantum gates interacting the data block with the ancilla qubits. And the second step is we measure the ancilla qubits. I guess then there's a third step, which is we do some classical deduction to figure out what the error is. But let's do the first step. And the first step, well, remember, we're going to just use the same gates that we would do if it were a Pauli error. OK? So if there were a Pauli error, and that procedure, if we have the state psi, that means there's no error. And so the syndrome should say that there's no error. OK? So this state here should go to psi tensor no error. And this state here, zj psi, well, we were supposed to figure out what the error is. This is a z error, so that's something that this decoding procedure can do. And so the syndrome is going to say, oh, there's an error z on qubit j. OK? And we have the superposition of these 2 things, so by linearity, it should go to the superposition. We should have this state. OK? Everyone comfortable with that?
So what was it you wrote over there on the left?
Unitaries. So this is the first step of the error correction procedure. OK, so now the next step is to measure. And so what do we get? Well, for this state, there's 2 possibilities, right? So one possibility is that we'll see the error syndrome no error. And the other possibility is that we'll see the error syndrome that's zj. And so what are the probabilities of these 2 things? So I guess I could say that these 2 states of the ancilla qubits are orthogonal, right? So one of them might be all zeros, and one of them might have some ones in it. OK? So they're orthogonal, so we really are getting those 2 possible outcomes. And the probability of this is cosine squared theta. And the probability of this is sine squared theta. OK? And moreover, we have, at this point, we have an entangled state between the system and the ancilla. And so when we measure the ancilla, we're collapsing that state. And so the remaining state on the system, in this case, is psi. That's what we had here. And in this case, it's zj psi. OK? So look what's happened. If we got the no error outcome, the state has collapsed, and there's now no error. If we got the outcome, the error is zj, the state is collapsed, and the error is now zj. So by pretending it was really a Pauli error and just acting as though it were, making measurements as though it were, we've made that really true. It's a triumph of wishful thinking. By measuring in terms of Pauli errors, we collapse the state, collapse the error until it actually is a Pauli error. OK? OK. And so that's going to solve problem 4. So I haven't quite told you how yet, but it's the sorry, this is one. But that same argument, you see, there wasn't really anything specific about this particular superposition, right? If we had an error that's a superposition of any matrices, any Paulis, then we would correct that as well in just the same way. So there's a general theorem So if a quantum error correcting code, so that's what these letters stand for, quantum error correcting code, corrects errors A and B, then it also corrects alpha A plus beta B. Okay? By basically that argument. And as a corollary, a quantum error correcting code that corrects I, X, Y, Z therefore corrects arbitrary single qubit errors. Why is that? Well, an arbitrary single qubit error, certainly a unitary, let's focus on the unitaries first. A unitary can be written, it's a 2 by 2 matrix, it's acting on a single qubit, so it can be written as a superposition of I, X, Y, and Z, because they form a basis for the space of 2 by 2 matrices. Okay? And so if we correct I, X, Y, and Z, by the theorem we correct any superposition of those, therefore arbitrary unitaries. Now what happens if we have some decohering error, right? Some arbitrary CP map. That's the most general thing that can happen to a single qubit. So rho is going to sum over k, ak rho, ak dagger. Okay? Now the AKs are also 2 by 2 matrices. So you can think of this as with some probability. So suppose rho here is a pure state, psi. So with some probability, psi goes to ak psi. And that's not totally fair because the probability depends on the state that you started with, but it's still basically true. Okay? So the point is that we started with psi, and now we have some mixture, probabilistic mixture of these different AK psis. And AK is a 2 by 2 matrix. And so our quantum error corrected code will correct that. Right? So the QECC will collapse it to some Pauli, and then we'll be able to correct it back to the state psi. And since that's true for any AK, no matter what k is, we're correcting this single qubit CP map. Okay? And so the upshot is that this 9-qubit code, since it corrects I, X, Y, and Z, corrects arbitrary single qubit errors, which was this problem 4 here. Okay? So are there any questions on that? OK, so let me then make one additional comment about this. So, OK, so first of all, two additional comments. So first of all, if you want to get a code that corrects many errors, then what you should do is you should correct Paulis on on many qubits. So if you correct t-qubit Paulis, then it corrects arbitrary t-qubit errors. And the reason is just the same, that you can write an arbitrary, that the t-qubit Paulis form basis for the space of 2 to the t by 2 to the t matrices. So you can get correct anything that happens on those t qubits. Yeah?
T qubits.
t qubits. So you have, let's say, I want to correct 3 qubits, right? So you say, OK, suppose there's an error on qubits 1, 2, and 7. Could be anything that happens on those 3 qubits. T is just, a variable. OK? So I guess the second comment was, suppose that we have a slightly different situation, which is also a totally reasonable one, which is that every qubit is getting a small unitary rotation, or non-unitary for that matter. OK? So that seems like maybe it doesn't fit into this framework, right? Because every qubit is getting an error, as opposed to just 1 qubit or 3 qubits. But this theorem still applies. OK? So suppose, for instance, that we have a unitary u, which is I plus epsilon e on every qubit. OK? So what's the state that we get out of that? Well, we're applying u tensor n to psi. And we can expand in terms of epsilon. Epsilon is going to be small, because this is a unitary that's close to the identity. And so what do we get? Well, the I term gives us psi back. And then we get an ordered epsilon term, which has e on the first qubit, plus e on the second qubit, plus e on the third qubit, and so on. And then we have an epsilon squared term, which looks like, e on the first qubit and on the second qubit, and e on the first and third qubits, and so on, and epsilon cubed, and so on. OK? But by linearity and by that theorem, we have a code that corrects arbitrary single qubit errors. And so that will take this. Well, this state psi will, of course, be corrected. That's no error. And this term here, that just has single qubit errors. And we can correct the superposition of them, even though they're on different qubits, right, by that theorem. And so this state will get corrected back to the right thing, to psi. Now this thing here, that has 2 qubit errors. And this code may not correct that. But this thing is just order epsilon squared. And so the state after error correction will be within O of epsilon squared of the correct state. And so once again, we're in this situation where, OK, sure, the error correction is not completely eliminating the errors. But when epsilon is small, it is reducing them. OK? Now, how small it has to be, well, there's a combinatoric factor here, right? Because there's n choose 2 terms here. And so exactly, and maybe some of them are corrected. And there's various different things that can happen. Some of them might be small. Some of them might not. But so there's some combinatoric factor there. But when epsilon is small enough, certainly these higher order terms that are not corrected are smaller than the terms that are corrected. And in particular, they're smaller than what we would have gotten if we had not done error correction at all, which would have an error that's order epsilon. OK? So error correction, quantum error correction, and it's the same quantum error correction codes like this 9-qubit code, will still reduce the error rate in this context. OK? So are there any questions? Yeah.
These codes works in practice in the current implementations of quantum computers?
Yeah. So people have experimentally demonstrated quantum error correcting codes. Now the catch, of course, is that the gates they're using are not perfect. So when you say, oh, so this 3-qubit code, for instance, has been done very many times, the 3-qubit phase code. And so you say, when you make this code, well, it's not, the state you get is not exactly alpha plus beta minus minus minus. There's some error in that. So if you just encode and then immediately decode, you'll see some error rate that'll be worse than if you hadn't done anything. But if you encode and then you wait a while, so that phase errors from decoherence T2 time starts to become an issue, then it gets better. So what you'll see is, so this is perfect fidelity. And so if you yeah, I'm trying to think if I should draw this on a log plot or not. But so this is fidelity to the right state, or error rate. So if you don't do error correction, you'll see something that looks like this. It'll eventually asymptote to, well, not to 0 actually, because random state still has fidelity half. But if you do error correction, it instead looks something like this, where it's not, at time 0, it's not 1, because there's those errors from the gates. But the slope here is smaller. Or so after a certain amount of time, the fidelity is definitely better doing error correction than not doing error correction. And that experiment has been done in a wide variety of systems. OK? Any other questions? OK, so tomorrow we'll continue to talk about error correction, some more of the kind of general principles and framework of quantum error correcting codes, and just give you a very, 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 very brief introduction to fault tolerance.